Water is unique. Why is water unique? Well, when we look at water and we look at trends and we look at what the chemical composition of water is, we'd actually expect to see different properties of water than what we see. And so going back to those intermolecular forces, the intermolecular forces contained in water are actually the driving force behind what makes water so unique. So let's take a look at this, just as a brief look here. Water doesn't have any odor, color, or really any taste at ordinary room temperatures. It occurs naturally as a liquid. We would not expect it to occur naturally as a liquid. And in fact, it's the only inorganic compound that occurs naturally as a liquid. Composes most of the mass of living organisms, not just humans, but our other living organisms as well. Water dissolves a lot of stuff. That's what we mean by it's an excellent solvent for many things. So I can put stuff in water and it dissolves a lot of different things. High number of things. The melting point and the boiling point of water are actually also abnormally high. I'm going to show you in a little bit a graph comparing water to other hydrogen-containing compounds that exist in the same group that oxygen does on the periodic table. And we can extrapolate where we would expect the boiling point of water to be compared to where it actually is. And we're going to see some similar behavior with a hydrogen compound, or hydrogen-nitrogen compound, ammonia, and with hydrogen and fluorine, hydrogen fluoride. So it's actually, there's some interesting things that are going on. The other crazy thing is if I go from the liquid state to the solid state of something, what I would expect is for the solid state to sink, because solids are typically more dense than liquids. However, the solid state of water is less dense than the liquid state, which is why ice floats. So that's also really unusual. Water has high surface tension and has a really high what we call specific heat, which I'll explain that toward the end of this section of this. So water is unique. I mean, the word unique sometimes is overused, but water actually really is like legitimately unique. So why is water so unique? It has to do with this intermolecular force called hydrogen bonding, right? So hydrogen bonding is this tether that holds water molecules together. So what is hydrogen bonding? Well, to understand hydrogen bonding, first we need to talk about something called electronegativity, all right? So electro, dealing with our electrons, negativity, dealing with the fact that like our electrons are negative here. So what is electronegativity? Electronegativity is basically electron greed, okay? So electronegativity, electron greed, okay? The more electronegative something is, the stronger it attracts electrons toward itself. Now, water has a formula of H2O. So I have 2 hydrogens and 1 oxygen in a water molecule. Oxygen is over here with electronegativity, okay? It is our second most electronegative element. The most electronegative element is fluorine, but oxygen is our second most electronegative element, okay? Which means that oxygen has a really, really, really strong capability to attract electrons to itself, which gives rise to something called polarity. When we have differences in electronegativity and we have a covalent bond, okay, we get something called a polar bond. So, more electronegative element attracts electrons to itself stronger. When we have a polar bond, we have an unequal sharing of electrons. So, when I have hydrogen bonded to oxygen, okay, oxygen's more electronegative, so oxygen's going to pull the electrons toward itself more strongly. The electrons are still contained in that hydrogen-oxygen bond, okay? So oxygen hasn't completely removed all the electrons to itself. It's just the electrons spend more time hanging out with oxygen than they do hanging out with hydrogen, because oxygen attracts them more strongly. And so what ends up happening is we get this partial positive on our hydrogen and this partial negative, not a full charge. They're not ions. We haven't completely transferred the electrons. All we've done is we've had a situation where they're attracted more strongly to one over the other. Okay? So we get what is called a polar bond when we have this unequal sharing of electrons. The greater that difference in electronegativity, the more polar the bond. Okay? So when we look at the difference in electronegativity, basically if we have little to no difference in electronegativity, we have what we call a pure or non-polar covalent bond. And that's usually situations where I have two of the same things bonded together. Like if I have a chlorine molecule, which is Cl2, chlorine and chlorine bonded together, I shouldn't have any difference in electronegativity because two identical chlorines, I'm not going to have a difference in electronegativity because they're exactly the same. But when I have a covalent bond that has a decent difference in electronegativity, that's where I get the polar covalent bond. And then when we have a very large difference in electronegativity, that's where we get that full transfer of electrons and we have an ionic bond. And so when we look at our metals versus our nonmetals, our metals have much lower electronegativity values. Our nonmetals have much higher electronegativity values, which is why we get that ionic bonding between metals and nonmetals, because our nonmetals attract the electrons so strongly with their high electronegativity that we end up pulling the electron completely off the metal and forming the cation and the anion, and we get the ionic bond. But between nonmetals and nonmetals, they have closer differences in electronegativity, which is where we are seeing the polar covalent bonds. It's not strong enough to completely yank the electron off the other species, but it's strong enough to say, hey, I want you, come hang out with me more. It's like if you've got two teams playing tug of war, the stronger team tugs that center line over much further and much more frequently than the weaker team does. And that's what we get with our difference in electronegativity. Okay? And so we have a decent electronegativity difference between oxygen and hydrogen. And so we also have to think about the shape of a molecule. All right? If I have something like carbon dioxide is what we call linear. Okay, it's a straight line. All right? So if I'm carbon, I have an oxygen here and I have an oxygen here. Now, the carbon-oxygen bond is polar. But if I have a straight line, I'm being pulled one direction, I'm being pulled another direction by the exact same thing, it kind of evens out, right? I have an equal strength of pulling from both sides. So overall, my molecule is non-polar. But water, okay? Water is bent. So if I'm an oxygen here, all right, hydrogen's down here, another hydrogen's down here, okay? Oxygen's pulling the electron density up, and then I have some electrons that are hanging out up here. And so that bent nature means I've got this angle, you can see in this diagram up here, I've got the angle that goes up this way, I've got the angle that goes up this way, they converge on each other, that pull, and so we get a net pull of electrons going up through that, and so we have a polar molecule. All right, so the bent shape of water and the polar nature of water is going to lead us to this strong intermolecular force called a hydrogen bond. All right, so we only get hydrogen bonding between molecules that have a hydrogen atom bonded to a small, highly electronegative atom that has lone pairs. These three small, highly electronegative atoms with lone pairs are fluorine, oxygen, and nitrogen, okay? And so a hydrogen bond is not an actual full bond. It's an intermolecular force. It's a molecular tether. And so if I have a partial positive and a partial negative with all these lone pairs, what's happening here? Okay, so oxygen being electronegative and attracting electrons more strongly, what that means is the electrons contained in that oxygen-hydrogen bond spend more time with the oxygen. That's why oxygen has the partial negative on it. So oxygen is flush with electrons. flush with this negative charge. Oxygen's super happy this way, super flush, super electronegative, super electron rich, yay electrons. Hydrogen, on the other hand, though, it's not very electronegative. It doesn't attract them very strongly. So when oxygen yanks all that electron density away from hydrogen, hydrogen's left going, wait a second, we're supposed to be sharing these electrons. I need that electron density too. I need some of that negative charge. Where is it? Well, it's hanging out with oxygen. So then along comes another water molecule with one of those really, really rich electron full oxygens. And that hydrogen that's missing a lot of that electron density goes, hey, can I hang out with you? You seem to have an excess of these electrons, and my oxygen stole all the electrons away from me. And that oxygen goes, sure, hang out with me. And so they form this tether. Now, what's cool about water, all right, in comparison to, say, nitrogen or fluorine, is oxygen has 2 lone pairs and 2 hydrogens. It takes a hydrogen and a lone pair to form a hydrogen bond. So if I have 2 and 2, I can get 4 simultaneous hydrogen bonds across every single water molecule. 1 hydrogen bond is decent. 2 hydrogen bonds is great. 3 is even better. 4 is extra strong. Meaning, if I were to try to boil water, I don't just have to break 1 tether per water molecule. I have to break 4. I have to sever 4 separate tethers to every single water molecule. Whereas nitrogen is not quite the same, all right? Nitrogen over here, as you can see, okay, this ammonia, we do form the hydrogen bond, but nitrogen, when it makes ammonia, has 1 lone pair and 3 hydrogens. So I can get a couple simultaneous hydrogen bonds across every ammonia, but I can't get 4 because I have an uneven number. I have 3 and 1. That's not going to be sustainable. Same thing with hydrogen fluoride, except opposite. I have 1 hydrogen and 3 lone pairs. So I can get a couple simultaneous hydrogen bonds to each hydrogen fluoride or each ammonia. That's it. I can't get any more than that across the entire sample. Unlike with water, because I have 2 lone pairs and 2 hydrogens, I can get 4 simultaneous hydrogen bonds across the entire sample, which makes for a very strong tether. Okay? And so you can start to see these hydrogen bonds. Now, in these images, unfortunately, they are shown with dotted lines. Okay? I actually studied what is called redox-dependent hydrogen bonding for years. And so when we drew hydrogen bonds, because the dots look way too much like electrons, when we drew hydrogen bonds, we always drew them like this. I'll show you. We drew them with dashed lines like that, just because that was the convention that most people studying what we did drew them. So if I ever draw them, I'm going to draw them with dashed lines instead of dots. It's the same thing. Okay? All right, and so, you know, we can keep getting this array of hydrogen bonding. So I could actually, let's see here. Let's put a couple more in here. All right, then let's put in another one right here. Okay. Put the lone pairs on these oxygens. We need those electrons for the hydrogen bond. I can put another one in over here. And I can just keep going. All right, I can get this array of 4 simultaneous hydrogen bonds to every single water molecule. Okay, so what does that mean? Well, it explains the abnormally high boiling point of water. So what do we know about water? Hopefully most of you are familiar with the fact that water boils at 100 degrees Celsius, or 212 Fahrenheit. That's really high. If we compare water to the other hydrogen-containing compounds in group 6A, all right, we would expect the boiling point of water to be closer to negative 100 degrees Celsius. Here's a graph. Okay, the dotted line, this right here, that is where the expected boiling point of water is if it followed the same trend as the hydrogen telluride, hydrogen selenide, and hydrogen sulfide. We see a little bit of the same thing with our ammonia and our hydrogen fluoride. You can see the blue lines and the green lines. If we kept going down, we would expect ammonia and hydrogen fluoride to also have much lower boiling points. But the drastic difference is much higher in water because, again, water has 4 simultaneous hydrogen bonds across every single molecule, which makes the difference even bigger with water than it does with the other ones. Okay, now this hydrogen bonding also explains why ice floats. So what happens when an ice crystal forms is our water molecules arrange themselves to maximize this hydrogen bonding behavior. And so instead of getting a more densely packed solid, like pretty much every other solid, we get a solid that has little holes all throughout it. And so those little holes all throughout it make ice a little bit less dense and make it float. And so what we get is we get these like tetrahedral configurations that leave room for these air holes. And because we have room for these air holes, ice floats instead of sinks. Now, hydrogen bonds are cool. Just as an aside, it's not just water where hydrogen bonds are really important. Now, the actual hydrogen-oxygen bond in water is way stronger than the tether between the hydrogen and the oxygen and hydrogen bond. It's only about 10% of the strength of the actual bond. But what's cool is a lot of things behave the way they do because of hydrogen bonds. Adhesives, we get a lot of that with hydrogen bonding between the hydrogens in an adhesive and a hydroxide or hydroxyl group in the surface they're bonding to. Proteins, very dependent on hydrogen bonds. Cellulose, wood is strong because of a lot of hydrogen bonding. DNA, you may have learned in middle school or high school that DNA base pairs, you get the ATGC. Well, why do we get ATGC? We get it because of hydrogen bonding. Our adenine and thymine form 2 head-on simultaneous hydrogen bonds. Our cytosine and guanine also form head-on hydrogen bonds, and they form 3 of them. If I were to try to base pair the cytosine with the adenine, I wouldn't get such hydrogen bonding behavior. This oxygen and this hydrogen up here, so this one right here and this one right here, those would not hydrogen bond because that hydrogen is attached to a carbon. This nitrogen and this nitrogen, well, there's no hydrogen, so we wouldn't get a hydrogen bond. We might get a hydrogen bond between this nitrogen and that hydrogen, or this hydrogen and that nitrogen, but we wouldn't get the same level of nice, and these are, the other thing about these is these are very linear. So they're nice, straight, head-on hydrogen bonds, which makes it very strong. So that's why DNA base pairs the way it does, is because of hydrogen bonding. All right. And then proteins only work properly when they fold correctly. Misfolded proteins cause a whole host of issues. And so if the amino acids don't sequence correctly, the right things aren't in the right place for proteins to fold properly. There's a lot of things that hold proteins together, but one of them is hydrogen bonds. So the protein folding, when it gets to this quaternary structure, when it's in this 3-dimensional folded crazy shape thing, one of the things holding that together is hydrogen bonds. Okay? When I look at these 2 compounds here, all right, notice in the formula compound, they have the same formula. 2 carbons, 6 hydrogens, 1 oxygen, but they're arranged differently, all right? In ethanol, I have this end. in dimethyl ether, I have oxygen in the middle. So to get a hydrogen bond, the hydrogen has to also be attached to the nitrogen, the oxygen, or the fluorine. So in dimethyl ether, that's not the case. There's no hydrogen attached to the oxygen. So there are no hydrogen bonds. Okay, but our ethanol, I can get hydrogen bonds at this end here because I have a hydrogen attached to that oxygen. And so I get hydrogen bonds here. And so look at the difference in the boiling point, okay? Same exact formula. One boils at 78 degrees Celsius. The other one becomes a gas at negative 22. Huge difference, all right? And that's due to the fact that ethanol can form hydrogen bonds, which are much stronger tethers than the hydrogen bonds that can form in our dimethyl ether, okay? And then the last really unique thing about water is the specific heat capacity. So basically, specific heat capacity is this ability to absorb heat. So it's the amount of heat required to change 1 gram of a substance by 1 degree Celsius. The lower the specific heat capacity, the faster something warms up. The higher the specific heat capacity, the slower something warms up. The reverse is true too. The higher the specific heat capacity, the faster something will lose heat and cool down. The higher the specific heat capacity, the slower something will lose heat or cool down. So here are 3 substances, a couple of metals and water. Look at the heat capacity of water compared to aluminum and copper. It's much, much higher, okay? Takes 4.184 joules of energy to change 1 gram, which is not that much, of water by 1 degree Celsius. Doesn't take much energy, though, to change 1 gram of aluminum or 1 gram of copper. It takes a lot more energy to change water. And so the implications of this, if you think about it, if water had a low specific heat capacity, and we're mostly made of water, what's going to happen to us with temperature changes? We're going to feel them a lot more extremely. We wouldn't be able to buffer them. Neither would our planet. Our oceans act as giant heat sinks because it takes so long to raise 1 gram of water by 1 degree. This is why also if you have a pool or you have access to a pool, at the start of summer when we're coming out of the colder temperatures, the start of summer, it may be really hot outside, but that water in the pool is still really cold because it's going to take a long time of the weather being warmer for that water to start heating up more. And then likewise, the same thing. Like once the weather starts to cool down, that pool is going to retain heat a little bit longer because it's going to take a little bit longer to bleed that heat off because of this high specific heat capacity. We wouldn't expect water to have such a high specific heat capacity. Water has an unusually high specific heat capacity, which is good for us because otherwise life wouldn't be able to exist the way it exists if water had a lower specific heat capacity. So hopefully you understand now why water actually really is this really cool, really unique substance that kind of defies what we would have expected based on looking at other trends and properties of things around water. So water, super cool.